All right, we're looking at some true or false statements about entropy, which is the major concept that we dig into in chapter 19. And it's how we understand why K is K. That's where we're headed in this chapter. But first, we had some fairly theoretical, conceptual concepts to get into before we got to do the quantitative work. And we just need to know these. So our first statement is the reverse of a non-spontaneous process is, and then the options are spontaneous or reversible. And the option you're looking for here is spontaneous. And like the book ops like the book picture of spontaneous versus non-spontaneous is if I'm like holding an egg and drop it, that's really not an egg. Here's an egg, and I am holding it up off of the table, it will spontaneously drop once I let it go, but it will never spontaneously pick itself back up, reform, and come back up. Um, and so that's let's see. So essentially what we're seeing, it is non-spontaneous to go up the hill. Okay, but it is spontaneous to go down the hill. That these two, like if it is work to go one way up the hill, then going back the other way must have been spontaneous. And reversibility is this concept that's like hypothetical. What if we could do that? What if we could achieve that change without ever leaving equilibrium, without ever doing work? And that requires infinitesimally small changes, either in volume or temperature, but something that is essentially just a hypothetical idea that is still useful, especially in engineering. Okay, so going down the hill is spontaneous, and so therefore going up the hill is non-spontaneous. And I'm always reminded of like, I don't know if your generation of parents ever said this, but like, oh, I had to walk to school uphill both ways, right? Like that's impossible. You can't walk uphill in both ways. One way has to be up and one way has to be down. One way has to be spontaneous and one way has to be non-spontaneous. And these are real processes. So the sort of the conceptual processes that we talk about, those are just purely conceptual processes are the reversible, are when we make it reversible, right? Where I take our sledding hill and I stretch it out so long, like infinitely long, that like, yes, I can go from here to here without ever taking a step up because I've stretched it out so long. And of course, that's like kind of mind-boggling and doesn't land. But it's conceptually true, right? Like if I were to take an infinite number of infinitesimally small steps, eventually I'd make it up there without ever like it is conceptual, and not real. So what we're looking for here is that all real processes are irreversible. And that's the real sledding hill. That's where, like, in one direction, I don't have to do work, and in the other direction, I do have to do work. So as I go down the hill, right, if this is my sledding hill, if I go down, always worth drawing a terrible little picture. Might as well, and it's cold outside, so I put my hat on today. And why not indulge in some doodling? That's my scarf. I'm going down the hill. And in this direction, I don't expend any effort, right? Like I'm not working. Like the whole point of going sledding is that I get to have this fun ride down. And then the downside of sledding is that I have to walk my butt back up the hill, right? And I'm sweaty. I am expending any energy. Like that heat is leaving me. And so I get back to the top of the hill. And so positionally, I am in the same place, but now I'm different. And that's the definition of irreversible. I can't just go back up the hill and be the same person. And that's the same, that's true if we are going to apply this to a reaction that is spontaneous in one direction and non-spontaneous in the other. And then this last statement here, this is essentially the second law of thermodynamics. For a spontaneous process, delta S of the universe is always positive. And this is our oracle that is going to help us decide if something is spontaneous or non-spontaneous. Like, if in going that direction, the entropy of the universe increases, then that is a spontaneous process. And for some things, it's very trivial. Like, we know that if we put, like, this is my block of ice. If I put this out at, 50 degrees Celsius, we know that it will spontaneously melt, right? So it'll go from solid to liquid if I set it out there. Like, I don't need to show you that delta S of the universe for this process is positive because you already know it's spontaneous. But we start here and look at the changes for delta S of the universe for processes like these because we do have that intuition and we can quantitatively show that delta S of the universe increases. That's a positive change for a process like this. And we can never find ourselves in a situation where, so this means spontaneous, we by definition could never make it so that delta S of the universe is less than zero, we're negative, and have a spontaneous process. So I can make delta S of the universe less than zero in this situation, but that would require me turning the temperature down in my room to negative 30 degrees Celsius or something below zero. And so, yes, delta S of the universe is now less than zero, but we know that ice won't melt then. And so then it would be a non-spontaneous process. That's not going to happen. Okay, so again, it feels trivial. You all know and have an intuition for when ice melts and doesn't melt. And we use that because we can lean on that intuition to say, well, in those situations, delta S of the universe is greater than zero. And when it's too cold, it won't melt. And that's when delta S of the universe would have been negative.